Hi, good day, Sydney. Thank you for having me at LEOCONN. My name is Tobias Ponselter. I'm a PhD student and research associate at the Mobile Cloud Computing Research Group at TU Berlin and Einstein Center Digital Future Berlin. I'm also currently on an internship with Hewlett Packard Labs in California, which is why I can't be in Australia today. I'll be talking a bit about testing Leo Edge software systems in virtual testbeds today. And we have 50 minutes. And before I get into all the details and what all that means, I just want to give a brief outline of how we'll spend those 50 minutes. We'll have about 15 minutes of just introduction and some theory, mostly about Celestial, which is our tool for virtual testbeds of Leo Edge systems in the cloud. I know you've seen quite a lot about low Earth orbit satellite networks today, but I just want to briefly go over all the terminology again, just to make sure that we're on the same page. Then we'll go into practice more, and we'll walk through building something using Celestial to test something on a virtual testbed. And that should take about 25 to 30 minutes. And because this is a pre-recorded presentation, I can't take any questions during that time. So we'll move all the questions to a little Q&A for 5 to 10 minutes at the end. Let's move into the Leo Edge. Now, at this point, I know you've already seen some of these pictures, maybe. We know that during the last 2 years, there's been an increase in interest in low Earth orbit satellites, especially in low Earth orbit satellite networks. There's been many new players like SpaceX and Amazon and OneWeb coming up with these networks comprising hundreds of thousands of satellites to provide global broadband internet connections. And, you know, satellite networks themselves have been around for a while. Traditionally, you would, when you think of satellite internet, you would think of a geostationary satellite at like 35,000 kilometers in altitude over the Earth. So it would stay at a fixed point in sky for the entire duration of its lifetime. And that makes it very easy to just point your satellite dish at it and ping a signal off that. And because it's so high up, it has a great cone of coverage, so you can get access from literally everywhere with some constraints. The issue is that at that altitude, you have to deal with a lot of network latency, just because the satellites themselves are very far away from you. So if you care about network latency, which now that the internet is ubiquitous and it's quite important for life, right? Then you do care about network latency. So what you can do instead is pull those satellites close to Earth. And this is what we see with low Earth orbit satellites. So low Earth orbit in this case means 500 to 2,000 kilometers of altitude, which is much closer than geostationary. The issue is that you don't have that great cone of coverage anymore. So to reach the ground station that was previously reachable with just one satellite, you would need to use several satellites and hop between those satellites using something we call inter-satellite links. So those are links between two satellites. So from your home ground station, let's say, you just ping up, that signal gets transmitted over several inter-satellite links until you reach an uplink ground station that's connected to the internet, for example. That's a bit of a hardware and engineering challenge that seems to be overcome now, which is great. And that wasn't possible in the past. But it also introduces some medicinal challenges. And one of the things is that when you think, oh, you now have lower latency, that is correct to some part. But all the services that you use, they're still quite far away. So let's say you want to access an application service somewhere in the cloud. Say that cloud is either connected directly using an uplink dish, or it's just connected to the internet, and your service provider is also gives you internet, so you have that access to there. To access any application service running there, you would still need to go through the entire network, which, depending on physical distance, for example, can be quite the communication delay. What if we were able to put that application service a bit closer to you? Let's say on the satellite itself. What if we had servers on satellites that would run that application service? So you could have a shorter communication delay. You don't have to go through the entire point to point to point to point, inter-satellite link chain. Well, that sounds like a good idea, but in practice, it's probably hard to implement. Not just from the hardware engineering challenges and the hardware systems challenges, especially in space, but also from just the software side. If you run an application like this, there's a few things you have to think about, right? You have to consider mobility, you have to consider coverage of the satellites, resource constraints, fault tolerance if a satellite server fails, which could easily happen in space because it's not as easily shielded from radiation. You have to care about multi-tenancy and isolation and scalability, all of those things that apply in terrestrial edge, but even more so in the LEO edge. So if you think about running applications through in some way on low Earth orbit satellites that are equipped with compute resources, you really have to tailor your application to cover all of those challenges, which is not really the best. What we can do instead is offer something like a compute platform that would abstract away from all the satellites and satellite compute resources. And this is a very interesting research area because there's quite a few ways to do this and quite a few different approaches to cover all of those challenges. But if we as researchers want to test something regarding those compute platforms, we don't really have an easy time because we don't easily have access to satellites with compute resources, right? So what we want to do instead is be able to run those on emulated testbeds. So have the option to prototype platforms, to test platforms, and to test applications on top of platforms, all without leaving Earth, without going to real satellites, because that can get quite expensive, and it's not that scalable. So we came up with a system that would help us in that, called Celestial. Our goal was to run cheap, emphasis on cheap, testbeds of LEO edge constellations in the cloud. So very cost effective. For each of the satellites, we want to provide isolated computing resources in a scalable manner. Scalable, again, is what makes this cost efficient and would let us test something at scale. And we want to provide support for arbitrary software systems, including platforms. This is important because we don't want our testbed tooling to interfere with what kinds of platforms we can run on it and we can test. So if we want to run containers, we want to be able to do that without changing our testbed infrastructure. And of course, we want to have efficiency, accuracy, reproducibility, and repeatability, as in all kinds of tests we do. So when you hear cheap, but also thousands of satellite servers, that sounds like a contradiction. And if we look at what we have available to achieve something like this in the cloud, it's not too great. So on the one hand, we have VMs, which provide high isolation, which is good, and they have the software support that we need. But they're quite costly, and they always have that overhead that we don't want to have when we want to run something at scale, especially at thousands. On the other hand, we have containers, which are low cost. You can easily co-locate them. They have low overhead, but they don't really provide the kinds of isolation that we would want. And the software support is limited. It's quite difficult to run containers within containers. And we would need to change our platform just for that test, but we don't have that standard environment that we would have on any VM, for example. So what we can use instead is something that's very recent, that sits kind of in the middle, and that's micro VMs. So micro VMs are very small VMs, as the name implies, that provide all the isolation and software support from real large VMs, but they're low cost and they have low overhead. Low cost meaning that we can co-locate them on cloud machines. We don't have to boot up an entire cloud machine just for one satellite server. So we can run hundreds of them on one larger cloud machine, which is much more cost efficient. The other thing is that maybe thousands isn't even necessary for the kinds of things we want to test. Let's look at this application. We have a collaborative application between 3 users located in this geographical area, and we want to test something either maybe we want to test a platform that migrates something across satellite service, or we want to test handoff for application as the satellites move. In any case, normally we care about satellites that are close by to that geographical area, because that's the potential server that we might want to use to run something. And let's say we have these 4 satellites as potential satellite servers that we want to look at and that we want to test and that we want to hand off between. So we really only care about these 4, right? Because these are close by. But if we emulate this, we have thousands of satellites, not just in this area, but also very far away. And we might care about the network connection in this area, but compute resources we only really need here. So what we do is we introduce a bounding box. In that bounding box, we can place any on Earth. For example, here we have 3 clients in West Africa. So we would just make our bounding box large enough to cover all the possible satellites that we would need to emulate. And we just limit emulation to those. And now we can emulate everything that could possibly be relevant for our tests and just not emulate the others, saving us a lot of costs and a lot of VMs that we have to run. The challenge here is that those satellites, they move and they move quickly. So at any second, one of the satellites could move out of the bounding box and the new possible satellite server moves into the bounding box. So we would need to account for that. And micro VMs give us the possibility to very quickly shut off and reboot a VM or restart it and unsuspend it, bring it back to life. And that's great because it saves us a lot of cost and it makes our life much easier. So this is what Celestial looks like. There's 3 main components that we have to consider. First, we have a coordinator. That's the heart of any emulation run. So within that, we have a network simulator that calculates the position of all the satellites, network connections between them, network parameters when they pass between different endpoints. And it does that in real time as we move through the emulation. Then we have a database that is populated by all the real-time data that comes out of the simulation. And we have the machine manager that is distributed across the coordinator and all the hosts that we have. And each of the hosts, and you can have as many as you like, runs a part of the machine manager and uses that to run all the micro VMs for our satellite service. So these micro VMs, depending on how many you have, which again depends on how many satellites you're emulating, they're distributed evenly across our hosts. And they just run there and they're updated by the machine manager, depending on whether they're suspended or not, whether they have any faults, whether they should emulate any faults. And they provide all the network connections between the satellites, which are again emulated to reflect network distance, network delay, bandwidth, etc. As input files to everything, we just need 3 things. We have file systems and kernels for micro VMs, which sounds a bit intimidating, but it's actually quite easy, as we'll walk through in the practice session. And we have a configuration file, which has all the parameters for emulation. That would have the network characteristics that we want. It would have the host configs. It would have the satellite constellation parameters, everything we need to repeat an experiment. Fitting Celestial into the entire Leo tooling ecosystem, and I hope I don't offend anyone, especially of the authors who I know are in the audience today. We have things moving toward accuracy on one side and scalability on the other. So if we look at simulation tooling, that's highly scalable, but accuracy is kind of limited as we can't really run real applications on it. On the other hand, if we are looking at something like the Tiansun constellation, that's highly accurate, right? Because you have real satellites in space. But scalability is limited because it's quite costly and you have to timeshare to do your measurements and everything. So we're really targeting that middle ground between having scalability, but also being sufficiently accurate that you can run it with some confidence that your real applications work as intended. And on the spectrum of computing and networking, we're moving more towards the compute side. So if your interest is more networking, maybe a different tool is a better option. But if you want to test compute applications and compute platforms, then Celestial might be a good option. If you want to learn more about Celestial, just from the theory, right? We have a paper coming up that's an archive. We have our code all open source, and we have documentation, of course. And we have this tutorial, which we'll go into practice now. And it should be on YouTube later if you want to catch up with something or repeat something or just look at what we did today, if you missed any of the specifics. And with that, I think we're through the theory part, and we can move into practice. So, to give you an overview of how Celestial works and how you can use it to run your applications, let's start with something that's a bit small, a small example application. And we have all of this documented on in the documentation of Celestial, but I want to walk through that a bit and give some context on what we do and how we do it, just so you know how that would apply to your own applications, and to let you see what the entire workflow looks like. So example application is a simple ground station server, single ground station server running in Berlin, for example, and just pinging satellites using standard ICMP pings. Just to check if the simulation that we have running at the core of the emulation, that the network parameters that we get out of that simulation, if they correctly apply in our emulation, if we can measure the same kind of network characteristics regarding network delays within the emulated testbeds, which should be accurate, right? So we'll be using a 72 orbit with 22 satellites per orbit satellite constellation, 550 kilometers altitude, 53 degrees inclination. That's standard plus grid topology. If this seems to me, this is the first shell of the proposed Starlink constellation, but we just need any example we'll do here. So we'll just do a single shell for now. And that little picture you see at the bottom, that is generated by the animation that we have, and I'll show that in a second. So you see what that constellation and that ground station would look like. And if we run this application in Celestial, this is the architecture that we have and that we'll be using now. So we're running all of this on Google Cloud. You can use whatever you want. Google Cloud is the simplest to use in this case because we have everything set up for that. But if you have your own service, then please go ahead and install on that. So we'll have our local machine from which we start everything. And we'll be running a Celestial coordinator that runs the simulation using Docker. That's quite helpful because it capsules, like it then containerizes, right, all the dependencies that we have for our coordinator, which is normally a hassle in Python. And we'll be using two host machines that are running Firecracker and our satellite service, and one of them will be hosting the ground station server that we have. They have a shared network plane, so all the servers can connect to each other and talk to each other, and each of them will be running the Celestial host binary. And that's only a single binary. We don't really need Docker for that. So that keeps the hosts limited. So let's dive into how that will work. So here we are. That's our local machine. We have Celestial checked out from Git, and let's see what the files look like. So here we have our code base. And you'll see we have a few different things that's all in one repository. And we'll be looking at the quick start today. So the quick start has three different things. We have an analysis that will be relevant later at the end. We have a Terraform folder that will help us create all the topology, all the hosts in Google Cloud in this case, just to get started, because otherwise it's quite a bit of manual effort to get all the cloud VMs running, right, and set them up. And the validator is the application that we'll be running. And again, there's a few components to that. We have two types of service. We have the ground station that runs the actual validation and pinging and everything. And we have the satellite service, which is just responding to the pings. So the server is really simple. It's just a single script that just runs forever and loops forever. And that's all we need to have the server running in the background, basically, so it doesn't shut down when an application would get to the end of its lifetime. So that's pretty simple. For the validator, we have a few different kinds of scripts that we want to use. We have a base script, which will help us install everything, all the dependencies. So that would be executed when we use our toolchain to generate the base file system for this machine. This is fairly simple. We just install Python, curl, like the dependencies that we need. So we can later install all the Python dependencies, because the validation script that we're running within that ground station micro VM is actually a little Python script. And that Python script uses the ping3 library to just ping service, random service. It's using just HTTP to a celestial database to get all the information about the current constellation. And it basically picks a few active satellites that are in reach and a few non-active satellites. So if we move down here, so we'll just ping these, I think it's just one satellite that's normally inactive for the duration of that lifetime, just to double check that if we ping that inactive satellite, it shouldn't be reachable, right? And we add some random satellites as well. We add some, and then like satellites that we can just access directly from the ground station because they're in line of sight, for example. And then we just loop forever, get the active satellites and ping all of them and just write it to a CSV file at the end. So that's fairly simple Python script to just get the state of the constellation, ping everything and write that down. So, and to run that, we have a little shell script again that will just at the end run that. It loops forever, so our ground station also doesn't stop. It just does it until we say, okay, we have enough data and we can go into analysis. This validator.toml file is our configuration file for the entire emulation. So that has everything in it that we would need to repeat this execution. We can specify a bounding box. We can specify an interval, let's say 1 second, like every second update our emulation testbed. We'll be using 2 hosts, and these are just static IP addresses. We also have an internal network that they can find each other on. We'll be using the database, and we can specify some additional SUP4 parameters if we want to, and some network parameters. The basic things will be fine. It just that in this case, like if you want to change something, you could. Our service will be running like on one vCPU, which we can specify for each micro VM. Specify memory, how large we want this to be, and everything. What kind of kernel and what root file system we want to use. We have this shell part, which like specifies how our shell or our constellation looks like. You can specify as many shells as you want. So in this case, we only have one, so that's why we only have one of these parameter sets. And of course, we have a ground station, which is running at these coordinates, which is our office in Berlin. So that's the basics of this parameter file. And all these files you see here, this is basically what constitutes our application. So that's all we need to just run this simple thing. If you have larger applications, of course, you can include any binaries here. You can include any additional dependencies that you would need. You can locally build your file system that you would then at the end run in your emulation. That's basically what we're doing here. So let's go back to our terminal and just do the animation real quick. So this is running on my local machine, so it's fairly easy. All the dependencies here are installed, and we of course had that documented. So if we just run Python and run our little animation script and point it to the configuration file that we have, so that's a quick start validator, and it's called validator.tml. If we just run that, that will start Celestial on a local host and just run a little animation. And you can just, whatever kind of application you write or whatever kind of parameters you have, see what that would look like. Because if you run like a few hundred micro VMs, it can be a bit intimidating, and it feels like you don't really have that access that you need and that overview of what you're actually running. So this is just visualizing what we'll be running in just a few seconds now. So now if you want to run this at home or in the audience or later you see this recording, I'd recommend just checking out our documentation, which is here. It's also linked in our repository. and going to the, after reading all about it, right, going to the quick set section, and that will walk you through step by step and on what to do and what to execute to run this example application. And if you just go from there, you can start adapting and start including your own code, start including your own applications, start changing parameters if you want to. I'd say let's quickly run through that, just give some additional context on what we're actually doing here, and just see what happens when you create such an emulation and you do such an emulation run. So this is the machine that we'll be using to run everything from. And this is a very basic Ubuntu machine, nothing installed except for a few dependencies that are also documented in the quick set tutorial, which are Docker, Terraform, and Google Cloud. So now we can go on and just clone a repository, which is on GitHub. That would be github.com open forkstack/celestial. And go into that and start building Celestial. So building Celestial just means that we are building all the binaries that we need. We're building all the Docker containers that we need that package all the other dependencies that we would use to, for example, create the root file systems, from our scripts. Everything about that is like easily Dockerized. So you can go and use it wherever you are. And you don't need to install any giant list of dependencies, for example. First thing that we're doing is creating a little Docker image that has our development environment that helps us compile everything without installing any dependencies to our host, which, depending on when you're trying this, can change over time, for example, and we want to make sure we have a repeatable environment that everyone can use without installing anything and running into errors all the time. That's why we're using Docker. And when we have that, we have a repeatable development environment where we can compile our protocol buffers and the Celestial binaries that will later run on our hosts. Using this development environment image, we can now go and compile everything we need. Next, we're building our Celestial binary. That's the part of Celestial that later runs on our hosts and starts all the micro VMs and set up the network connection. We will just run that in Docker as well, just using our new development environment. And it takes a minute, downloads all the dependencies, and then compiles everything into a single binary. So now that that's done, we should see the Celestial binary in our folder. And there we are. That's the part that later runs on our host. The final thing we need to compile is a root file system bullet. So that will help us compile our application code, our scripts, into a root file system that we can use on our micro VMs. And that is also Dockerized because it has a few dependencies that, again, we don't want people to need to install. Great, so let's go into our application directly, which is in Quick Start and validate it. So here we can just use the image we just built to create our file system for our validator. And you will see that it has a few parameters. So we're running this rootfs builder Docker image, and we're running in privileged mode because it needs some privilege to create a root file system using some kernel APIs. And we just map all the files that we later want in our file system to the correct points in the root file system builder. There's documentation on that, but for now, I'll just note that anything that you add to files will later be on the root of the file system. So the Python script, for example, that will later just be the Python script in the file system. The validator shell script will add the app.sh, which means that that is executed when the root file system and the micro VM boots. And the base script is executed when we are building the file system. So that installs all the dependencies, and that doesn't happen during the emulation run. It happens right now as a bullet. So let's go and just build that. And at the end, you should see this. And if we look through the logs, we can see that at this point, it has created this root file system file for us using a squashfs file system. We were using squashfs because it helps us compress everything into as small an image as we can possibly have. And later, when we deploy it on Celestial, we're using that image for thousands of servers, for example, but we only need one copy because we have a copy on write file system in Celestial. So if any server wants to write a file to the file system, it actually has a separate buffer for that particular server. And that's where all the changes are written to. that makes it highly scalable. So even if you have thousands of servers, we don't need to copy 1 GB file system, for example, 1,000 times. We just have that one image, and then everything, all the changes on top of that are just written to a separate buffer. We also need a kernel, or a Linux kernel. We can build it ourselves, and it's surprisingly easy, and we have put a bit of documentation on how you would do that. If you want to use specific kernel features in your applications, for example, you want to enable containers for your micro VMs, or you want to enable some new form of migration, that's fairly easy. And it's a highly useful thing to have, as it turns out. Sometimes you just want to test a new kernel feature and you need something to build a specific feature into your application. And it's very nice to have the ability to just change the kernel that you're using without making Google angry, for example. Instead of building a kernel, for now, we'll just download one that Firecracker team kindly provides. So you can just use that to boot your Firecracker VMs. That's all the dependencies for that. But if you would want to change something, you could go and see their documentation, of course. So let's move back to a root directory and look for the Terraform directory in our quickstart folder. And the first thing that we're going to do is just initialize Terraform. We already have everything set up here, and if you follow the quick start documentation, you will also be at that part. So everything seems perfect. Now we just have to set a few parameters. In this case, I'm in the Celestial-LEOCONN project on Google Cloud. So I'll just have to set that so Terraform knows where to deploy my service. And I also want to use the Europe West 3 zone. And all I need to do is set GCP's region for that. Sorry. And the zone that we have is C. So if that looks good, which it does now, we can simply apply it using a similar thing, just Terraform apply, and it will ask us, do you want to do that? Yes, please. And it will go and start everything for you. There we go. All the resources have been added. We can confirm that everything's running correctly by just listing the instances that we have on Google Cloud. So let's see. And of course, we have Celestial coordinator and 2 hosts, host 0 and host 1. And you'll see that these internal IP addresses, although they're cut off here, they match what we had in our configuration file. So if your IP addresses are somewhat different because you're using custom infrastructure, just go and change the configuration file accordingly. Next, we'll need to upload all the artifacts. I'll just skip over that for now because it's just executing a few copy files, and you'll find copy commands and you'll find everything in the documentation. So here we are, 4 little terminals on our local machine. In that first terminal, I'm going to log into host 0, then host 1 in that second one, and the coordinator down here. And then we can run from those machines. So I'm just going to run Google Compute Cloud SSH. That's probably the simplest way to run over SSH without setting all the keys. The Celestial host 0 in here, and vCloud Compute SSH, Celestial host 1 in here, and the coordinator down here. And there we go. Now we have our windows to 3 different machines. And now we can just simply start our Celestial binary. And we want to do that as a root because we need access to KVM to start our micro VMs and change some system settings. I highly recommend not doing that locally, just because it messes with networking settings that it needs. So I'll just run it here. So now we're running our Celestial hosts. All we're waiting for is the coordinator to tell them what to do. Let's go and just start that. We're simply using that Celestial image that we built early in the process, and we're mapping our validator to this config file within that container. And that's what's used to run the coordinator, and that has all the dependencies and everything, and it has the network addresses to contact the hosts at their own same network. So we run that. We'll see some output. Configuration is added, which is great, as expected. All the ground stations are covered by the bounding box, so we don't have any ground station in Australia, for example. That's not covered by our bounding box in over Europe. And it will start that demanding startup process. So it's starting a few different micro-VMs already for the ground station that we have, and for all the satellite servers that are already active. And at the beginning, that's quite intense because it's starting a few servers. But later during the process, if we only change 1 or 2 servers per update, it's a bit quicker. And now nothing is running, so there's no emulation running. It's just starting the service, so I can start the emulation 1 step down. And there we are, it's already done. So it's updating as we speak, basically. It's updating in real time, it's updating all the networks. And depending on the size of your constellation and your host performance and how many micro VMs you have, that would change how the how long the update process takes. And while it's running, I think we should just wait a few minutes and see what the output is at the end and see what the graphs are and analyze if the validator found that all the ping responses and measured network delays match those of the simulation. And the good thing about this being a pre-recorded presentation is that I can just cut out our 20 minutes of waiting and just come back in 20 minutes and we'll see what the output is. So there we are. Our experiments have been running for about 20 minutes now. So we can just go ahead and stop them, just interrupting everything and collect our results. Everything's closed now. And since our validating script has written all the results and everything to the file system on a little file, we'll just have to mount that file system, pull out that file, and just copy it back to our local machine. And it's fairly easy because we're using standard Linux tooling. All we really need to do on host 0 in this case, because this is what's running, is mount that validator file system and copy out of validator CSV to our folder, unmount the file system if we want to use it in the future, and remove that thing again. So let's go back to our local machine and just copy that thing from our host. And we're using SCP over G-Cloud again, because that's a bit easier. So we now have this validator results file, and that's a new results from a validation one that we ran in our emulated testbed in the cloud, and it's the easiest stuff. We provide a little track validator, which generates a few graphs from that. So let's see. So we don't have Python installed on this machine, so we'll need to run a Docker again, but it's fairly simple. You'll just run a standard Python image and install the requirements, which we have here, which is just matplotlib and to generate some graphs. And we're running our track validator script, and that's using the validation CSV that we generated and pulled from our testbed. So this has installed everything and run our script, which is great. Let's see what we have in the graphs folder. And there we are, generated just today. It's October 9th today. We have 6 different graphs that we can look at and see, like, to visualize what the emulation did and to visualize what the validator measured, and comparing that to what we expected to happen, given what happened in the simulation. And that will help us determine how accurate the network emulation regarding network delay, at least, is in Celestial, and if it's worth running replications today, which hopefully it is, right? So I've downloaded all the graphs to our graphs folder. So let's see what it looks like. This is the expected line. So that's what a simulation is telling us we should expect to happen. So let's compare that to what's actually happened. And it looks fairly similar. And this is what you expect, right? The simulation, anything that comes out of that, anything that is expected regarding network overhead would show up in the emulation as well, and we can actually measure it. Notice that we have this 1E7 up here, which is the number we choose for any unreachable satellites. So you can't really go into too much detail on how accurate this is down here. Let's see instead this ECDF. And this is showing us the difference between what we measure and what we expect, and the proportion of how often it happens. So we see quite a few 0 and below that. And we see that about in like almost all of the cases, except for 1 or 2 measurements, we have a difference in what we measure to what we expect to measure of around like 2.5 to 3 milliseconds. And that's pretty good because remember that the simulation itself only measures physical distance. So it will put in, this is how much minimum network delay you should expect between these two machines. And while the micro VMs themselves actually also run anything on top of that. So anything that passes through the kernel and through the kernel network stack, anything on top of that that's processing through the ping library or variation in the network, that will reflect here, which it won't in a simulation because that's highly accurate, just doing what the physics tells it to do. So next step we have here just the satellites that are actually reachable at any point in time to that ground station, and the network delay that we expect to see. So that filters out all of those unreachable ones, kind of make the actual measurement and the reachable ones small on the first graph that we had. So you'll see these nice patterns here, which are caused by satellite motions. And you'll see that we have, depending on the satellite, we'll see increase, decrease over time. And then at some point, maybe it just drops out, it's not reachable anymore. So this is what we expect to happen based on the simulation. Let's look at the actual measurements that we took. You might actually think that it's the same graph, but there's a few differences here and there. But overall, it seems like it's fairly accurate. So if we move into this part, for example, this third to last hump, you'll see like a few differences in the details. For example, this line is connected to this one here. Well, here there's a bit of difference, and this one is horizontal, while this one is slightly shaped towards the bottom. So there's a few bits and pieces in the measurements, but overall it looks fairly similar and fairly it makes you confident that what you see in the simulation is actually what's supposed to happen to your systems. Of course, if that's what actually happens in a real satellite network, that's still up for debate. So if we get new measurements and new satellite networks come out and can measure them, and we have a better idea of what's happening, we can integrate that in your simulation and be sure that that's actually what we're also seeing in the emulation. And that's the part that this makes sure here. So I think that covers all the practice part. We've went from installing Celestial on the first machine, booting up a few cloud VMs, running Celestial on that, installing an application, running an emulated testbeds, getting results, and just analyzing these results real quick. And that quick start is just meant to get you started in running on Celestial. If you want to build your own applications, integrate your own software, you can do that. You can run it not just in Google Cloud, you can run it on any cloud, as long as it supports nested virtualization, as AWS, for example, does. Or you can just run it on your local machines, your local servers if you have any. And with that, I think that covers everything from my part, from my side. So we can move into questions. Thank you again for having me, and I'll be live for the live Q&A in just a second. Thank you.